Right, we're going to continue our video lesson on reversible reactions, and specifically in when reversible reactions are in equilibrium. Last lesson we talked about how reversible reactions got into equilibrium, and basically I'm going to draw the graph here real quickly. So at the beginning of the reaction, the rate of the forward reaction is really high. The rate of the forward reaction is really high, and then the rate of the backward reaction is quite low. Okay? And so what's going to happen is that when you start at the beginning reaction, you have the reactants, lots of reactants, and then they're going to make products, right? So the rate of the forward reaction is high, but there's not a lot of reactants here to go back, so the rate is low. But eventually you make more products, and some of the products are going to revert back into the reactants, and so the rate of the backward reaction goes up, and the rate of the forward reaction goes down because more reactants are forming products. And so the two rate is going to converge together or merge together, and the forward and backward rate of the reaction is going to be equal. And today we're going to talk about how we're going to change that equilibrium by manipulating some of the factors. And one scientist by the name of Chatelier, all right, I'm just going to write the name here. He's a French dude, so people are going to mispronounce it. Even I may be mispronouncing it, but this is how I learned to pronounce his name, Chatelier. And so he specifically states that when something is in equilibrium and you put stress on that equilibrium is going to respond to that stress and find a new balance again. And it's exactly like when you're standing still in the crowd and suddenly someone pushes you, you're going to wave your hands like, whoa, whoa, whoa. And you lose your balance just momentarily, and then you wave your hands, right? Because the stress is pushing you down, and then you react to that stress by waving your hands to find a new balance, and then you've found your balance again. So that is basically Le Chatelier's principle. There are basically three ways I'm going to discuss in how we affect this this equilibrium, and how these factors affect the equilibrium. And in your exams, you're going to be asked to predict what is going to happen to the reaction system, to the system, when you add stress to it. All right? So the three factors I'm going to talk about is concentration, temperature, and pressure. And then I'm going to slowly talk about the last one, which is catalyst. All right? Okay, so here we go. How would concentration affect the equilibrium? All right? Now, let's say we have a very happy system here. Blue molecules with orange molecules making pink molecules, okay? Or whatever, chemicals, all right? And they are in a closed vessel, and they are in equilibrium. So the forward rate is the same as the backward rate. So now, what happens if we change the concentration of one of these factors? For example, what happens if I add more blues into this reaction vessel and increase the concentration of blues? What's going to happen is that you put stress here, and in order to alleviate the stress, something is going to happen. So when you put stress here, right, the system is going to react by making more pinks. Now, why is that? Well, think of it in terms in the atomic environment, right? When you have lots more blues, the blues are moving around, colliding with each other or whatever, and there's lots of blues colliding with each other, but now you've increased the chance of blues colliding with orange as well, because there's lots of them colliding around. And so they're going to make more pink. All right? So that is one way you can affect the equilibrium So what if we add more orange? What's going to happen? Well, we're going to put more stress into the system, and in order to alleviate the stress has to go somewhere, and it does that by making more pinks. Okay? So you're going to be asked, what happens when I add more orange? You're going to say, well, if I add more orange, I'm going to get more products. That's basically what you're going to say. What if I add more of this pink? What's going to happen? You're going to put stress into the system here, and it's going to alleviate it by making more of these. Right? Okay. So the same is in reverse when we want to remove the concentration of one of these things. If you remove the concentration, you're pulling it out, you're adding stress to it, and so what's going to happen is that pink is going to form these two, and so this concentration is also going to go down. So when you put stress here, it's going to move, the pink is going to make more of this, and as a result, pink, the amount of pink has gone down. The concentration of pink has also gone down. And it's the same if you remove pink, what's going to happen to the system, that the system is now going to try to balance it by making more pink. And so you're going to make more pink, and as a result, you're going to also decrease the concentration of the blues and the orange. All right, so now you got the idea of what happens when you change the concentration of a reaction in a closed system. All right? So next one is about how we affect temperature. Now, when we add stress, change the temperature in a reaction, it all depends on whether it's an exothermic or endothermic reaction. So let's draw the energy profile, and let's assume that this reversible reaction is in fact an endothermic reaction. So you have the reactants over here. See, you can see it, the reactants over here, and it's an endothermic reaction, so the products are here. This is the activation energy, all right? Oh wait, this is the activation energy forward, and this is the activation energy backwards. All right, so this is an endothermic reaction. Now, in an endothermic reaction, when we increase the temperature, temperature is noted by this delta sign. This is temperature. If we increase the temperature, that means we take increasing the energy from here to somewhere here. What you're going to do is you are going to increase the yield of the products. Okay? If the reaction is an endothermic reaction, when we increase the temperature, you're going to increase the yield of the products. Now, if we decrease the temperature, that means the temperature energy is going to go down. What you're going to do is you're going to increase the yield of the reactants. Okay, not yield. The yield is just going to go down, basically. You're not going to make a lot of this. No, you're going to have a lot of this. Okay, so that is the effect of temperature on an endothermic system. Now, what if the reaction profile is an exothermic reaction? So here we have the energy profile again, and we have the reactant energy here, activation energy, and the products. All right, so here we go. If this was an exothermic reaction, when we increase the temperature, so we're going to move the temperature from down here to up here, what is going to happen is that you're going to increase the yield of the reactants. All right, this is going to be formed, and this is going to go down. All right, but if we decrease the temperature, the yield of the products is going to go up. Right. So decrease the energy, and the yield of the product is going to go up. So that is how temperature can affect the equilibrium. All right. So basically, when it's an exothermic reaction, when you put stress on the system, it's going to shift to make more reactants. When you remove stress from the system, when you decrease stress and you put stress on the opposite direction, you're going to make more products. The opposite is for endothermic, okay? So, it's all about the equilibrium reacting to the stress that has been placed on the system. Okay, so now that we have talked about concentration and temperature, these two factors can happen under, if these two reactions can happen whether the products or the reactants are solid, liquids, or gases. Okay, it doesn't matter whether the products or reactants are solid, liquids, or gases. These factors will affect this reversible reaction. But the third factor, pressure, is slightly different. Here, pressure, one of your reactants and or products has to be a gas, all right? If one of them is not a gas, then this changing the pressure will not do anything to this equilibrium. All right, so let's go. Now, when one of the reactants is a gas, or products is a gas, whichever it is, changing the pressure will affect the equilibrium in a slightly different manner. And you have to take into account of which side of the reaction, the left side or the right side, being more. So if you look at this reversible reaction, we have a blue and an orange making one thing. So two reactants making one product right here, all right? So you can change this to make it molecules or whatever, like N2 and H2 and NH3. Doesn't matter, okay? So I'm just saying. So here you have two molecules and here you have one molecule, all right? So what happens when you change the pressure is that pressure is going to go towards the part where it alleviates stress. So for example, if you increase the pressure of the system is going to favor the part of the reaction, the side of the reaction that has less molecules. So you increase the pressure, it's going to form more products. If you decrease the pressure, you're going to form more reactants. So let us talk about how to use, how to explain this at the atomic level. So you have a system, okay? You have a system, and this is your piston, all right? You have your molecules. If the vessel is open, because the pressure is open, then you're going to have more space. And so what's going to happen is that this big molecule is going to break up into smaller molecules because this smaller molecule happens to be more chaotic, right? There's more of it, and so it's just happier being there. But if you increase the pressure by lowering the piston, right, you're going to push and add stress into the system in here because now there's less volume. And what is going to happen is that the molecules have no space to go and it's going to start colliding more rapidly in this small amount of space, and it's going to make more disks because one of this occupies less space than two of this. You get it? So it's going to merge, it's going to combine and make pink, because there's less pink than there is blue and orange, because blue will occupy X amount of space, orange will occupy Y amount of space, but X and Y is going to occupy more space than this Z amount of space. All right, so it's going to come down and make that. All right, so if the reversible reaction happens to be, let's say, making this and this, so two of this reactors making three different types of products. So if you change the pressure, right? So this can be a classic example where one is CO2, one is H2O. Forget about the specific examples. Okay? So let's say the two reactors make three different products. So if you increase the pressure, what is going to happen is that there's three of these things on the right side and two on the left side. So the system is going to react to make more of these blue and orange. But if you decrease the pressure, that means you increase the volume of the vessel, it's going to make more of these. Okay? So that is how pressure can affect the equilibrium, depending on if one of these reactants or products happens to be a gas. All right. So finally, we're going to talk about how catalyst affects the equilibrium. Well, catalyst basically doesn't really affect, only affects the rate of reaction by making the forward reaction go fast or the backward reaction go fast. So catalysts don't really affect much in terms of how it changes the equilibrium, but if you have a forward-moving catalyst, you're definitely going to make more products. If you have a catalyst that prevents you, or an inhibitor prevents you from making products, then you're going to have more reactants, all right, or a backward-moving catalyst. So basically, catalyst is quite predictable in terms of what it's going to do. So normally, people don't really talk about that. So that's it. That is all I need to say about changes in equilibrium and the Chatelier principle. And we've learned about how changing temperature, concentration, and pressure affects the yield or the reactants or the products. So you should know how to predict what is going to be made when you put stress into a system. Next time, we're going to move on to redox.